I'm delighted to have Anoop Rao here from the Institute of Advanced Study. Anoop was a graduate student at UT Austin under David Zuckerman. When he was there, he did some seminal work on an area called randomness extraction, for which he won the Best Student Paper Award at Stock. Right now, he's doing a postdoc at the Institute for Advanced Study, where he's been doing a lot of very interesting work on hardness amplification that he's going to speak with us about today. And shame on those of you who sent me dirty jokes about the title of the talk. So without further ado, I'll leave you with Anoop.
Okay, thanks for having me. So I'm going to talk about hardness amplification by repetition. Hopefully, at the end of this talk, you'll know what most of the words on that slide mean. So let me start with an example that illustrates the kind of question that I'm interested in. Suppose you want to compute some function. Okay, so you want to compute this function f. And you have some application for this thing. So you go out and you spend a lot of time and put in a lot of effort to find the best possible way to compute this function. Okay? And here it is. You design this circuit. It's the circuit of your dreams. It consumes very little power, is very small, and computes your function beautifully. Okay, and let's say that this circuit of yours, this device, is a big success. Okay? So now everybody wants to compute this function. And there's a huge demand. People want to kind of compute your function en masse. People even want to compute multiple copies of the function at the same time. So here's one way in which you could satisfy this demand. Here's one way in which you could compute multiple copies of this function. You could just take the circuit that you designed for computing one copy of the function and just repeat it, right? So now you print out 4 copies of your original circuit. You end up with one big circuit that computes 4 copies of this function at the same time. And that's your solution. And the question I want to ask you is this always the best thing to do? Okay? So it could turn out, for instance, that actually there's a much smaller circuit that's more efficient, but still does the same job. Right? It takes 4 inputs and computes the function 4 times. Okay? And that's kind of the question that I'm interested in. The question is, can we save somehow by combining independent computations? Okay? And this is a question you could ask not just about circuits. You could ask it in any model of computation. The question is, can you save computational resources in whatever model of computation you're interested in looking at by combining independent computations? Okay, so let me throw it out to you. What do you think? Can you think of an example of a context where kind of computing k copies of something is not k times as expensive? Any ideas? Sure, okay. Okay, no. We ask, what's your example?
Well, if part of the computation is the same for the different inputs, then you could just do it once.
But then, okay, so that's right. But then this means that you could have hardwired part of the computation that you would have used in the original computation. So the question doesn't quite make so much sense from designing algorithms. But if you were designing a circuit, so one example that someone suggested to me before is you could think of like computing the Fibonacci numbers, like computing the kth Fibonacci number. And if you did this, you would think that if you have to compute many Fibonacci numbers, well, you've already stored a lot of numbers along the way, and so you don't have to repeat the computation. But actually, this is not a good example because you could have a really small circuit that does the initial computation just by hardwiring kind of paths along the way. Okay. Anyway, but you're right. It's yes.
Well, it's like what we do in image processing with the low-level convolution operators. The operator takes in a neighborhood of a certain size, and you're computing it every pixel in the image, but when you compute part of it for one pixel, you've got part of what you need for the next pixel. So that's used kind of standardly.
Okay.
But if you put in an entirely different image, I assume that's what you're going to say next.
Right.
Right. Then you generally wouldn't use the former partial sums from another image, although maybe you could.
Right. I am talking about completely independent inputs. Okay, so the inputs are completely different. But even with completely different inputs, actually what you guys are suggesting is kind of right. It turns out that if you're talking about circuits, you can save by combining computations. Let me give you an example that I know about. The example comes from matrix multiplication. So here's how it works. Suppose you want to just compute the linear function that's described by some matrix. Okay, so you have some fixed matrix A that's an n by n Boolean matrix in mind, and you want to take every input vector and multiply it with this matrix. Okay, so this gives you some fixed n bit output. And now if you think about how expensive it is to do this computation, it turns out that for any matrix A, you can do this computation with a circuit of size n squared. And in fact, there's some matrix for which you need a circuit that's at least n squared big. You can just show this by counting. You just kind of count the number of matrices there are. And there's so many of them that they cannot all have small circuits, circuits of size n squared. Okay, so there's some matrix A for which computing this product takes a circuit of size n squared. On the other hand, if you think about computing many copies of this function, okay, as I've suggestively arranged it, that's the same as multiplying this matrix A with an n by n input matrix, right? So every product, so this now computes n different products. Every column in the output just corresponds to multiplying the matrix A with the corresponding column in the input matrix. And we know how to do this kind of thing surprisingly well. Right? We have, starting with the work of Strassen, we know how to do this matrix product for an two n by n matrices in time something like n to the 2.376. This translates to a circuit of size n to the 2.376. So you see that this gives you a circuit that's actually a lot smaller than what you would have got if you took the circuit you started out with and just put n copies of it. Okay? So in some situations, you can save by combining computations that are completely independent. And that's kind of the theme today. I want to look at a couple of situations where you have this kind of question, where you have kind of independent things. And I'll ask the question, can we save by combining these independent computations? Now, this is not a new question. This kind of thing has been studied before. In particular, it's had applications in cryptography. Yao's XOR lemma is an example of this kind of question. In pseudo-randomness and in proving circuit lower bounds. Okay, but I'm going to look at a couple of areas where this kind of question has showed up that I've worked on. So here's what I'm going to tell you about for the rest of the talk. I'll first describe this kind of question in the context of communication complexity. I'll say what it has to do with hardness of amplification. And then I'll say what all this has taught me about bubbles. Okay. Okay, so the first part is about communication complexity. So what's communication complexity? So here we're interested in kind of studying how much two parties need to communicate with each other in order to achieve some common goal. So let's say you want to make an appointment at the doctor's office. So you get on the phone and you call the doctor's office and you say, I want to make an appointment. And you're trying to find a time that works for both you and the doctor. Okay, so the doctor, so one way in which this conversation could go, okay, is that the doctor could say, well, here are all the times that I'm free in the next 2 weeks. And after she reads out all these times, you could say, okay, here's a time that works for me. Right? That's one protocol for solving this problem. You see that it's not the best protocol. This is not what we do all the time. What we usually do is something much more efficient. What usually happens is somebody suggests a time. The other person responds, that doesn't quite work. How about this time? And then after a little back and forth, you eventually settle on something that works for both of you. Okay, so this is another protocol to solve the same problem, but it's much more efficient because we had to talk a lot less. In general, communication complexity measures how long the conversation has to be to compute an arbitrary function. Okay, so in general, each of the parties has some input that they know. The other party doesn't know this input. And they're interested in computing some joint function of their inputs. And to do this, they have a conversation. Right? So the first party might send a message that's a function only of their input. The second party would respond with another message that's a function of both their input and the past conversation. Okay, and in this way, at every step, someone says something more about their input and the past conversation. And eventually, somebody knows the answer. Somebody figures out what the value of the function is. Okay, this is what's called a communication protocol for computing this function. Okay. Now, the communication complexity of the function is just the length. It's exactly what you might think. It's what I've described to you is a deterministic communication protocol. And the deterministic communication complexity of a function is just the length of the shortest protocol that figures out the value of the function. Okay. Now you can also talk about randomized protocols. They're essentially the same thing, except now all the functions are allowed to be not just deterministic functions as inputs, but you allow the participants to use random bits and transmit things which are are distributions at every stage. Okay, in this case, again, we define the randomized communication complexity of a function to be just the length of the shortest protocol, which gets the answer right 90% of the time, say. Okay, so this is some measure of the complexity of computing this function. So let me give you an example. For example, let's look at the function where the equality function. So both parties have an n-bit string, and they're interested in knowing whether or not these strings are the same. So it turns out that it's easy to see that the deterministic communication complexity of figuring this out is n plus 1. You can't do anything better than just having one party just send their entire string over to the other party. But the randomized communication complexity is much smaller. In fact, you can do it in just a constant number of bits of communication. Okay, and the idea is really simple. You just have the parties randomly pick a hash function, okay, that can hash the entire input down to a few bits, and then you just have the parties check that the hashes are the same. Okay, so you kind of think that the parties know some common random hash function, and the first party just sends the hash of his string, and the second party just checks that the hash is equal to the hash of his own string. Okay, I mean, I just wanted to point this out to say that the randomized communication complexity can be very, very different from the deterministic communication complexity. It can be a lot smaller. Okay, so so the direct sum question. So before that, let me just say that, as you might imagine, communication is something that happens in many models of computation. And so kind of the study of communication complexity has led to results in many areas in computer science. Let me just give you one quick example. So for example, so here's how you can use communication complexity to say something about the structure of a circuit. So there's a circuit. What you can do is you can kind of just draw a line across the circuit and look at look at how the inputs feed into the circuit. So call all the inputs that feed in above the line x and all the inputs that feed in below the line y. And then you kind of see that you can view the computation that the circuit is doing as a communication between the two parts of the circuit, right? And this kind of tells you that the number of wires that cross this line are related to the communication. If you knew, for instance, that the communication complexity of the function that this circuit is computing is high, then that would tell you that the number of wires that have to cross this line must be high. Okay, so that's one way in which you could relate these two things. Okay. Okay, so returning to the question that we're interested in, it's the direct sum question. So now you want to compute not just one copy, but many copies of this function. We know the naive way to do this would be to just compute each one separately, right? You look at the first pair of inputs, run a protocol to compute that, then look at the second pair, run a protocol to compute that, and so on. And the question we want to ask is this really the best way to do this? Or is there some way to kind of combine the computations to do it better? All right, so let me tell you about what we know. So in the mid-90s, Fedor, Kushilevitz, Naor, and Nissan showed that for a right setting of parameters, the communication must grow. So they showed that if a single copy takes c bits of communication, then computing k copies takes at least k times square root c bits of communication. Okay, and then there was a lot of work on restricted cases trying to show the same kind of result for randomized communication for the more general model. And so there was a bunch of work, but no results for the completely general model. And last year, with Barak, Braverman, and Chen, we managed to show that if you want to compute k copies of your original function, the communication must grow by a factor of square root k. Okay? Okay, so let me just say a little bit about how you would try and prove something like this. So the basic idea is to get a reduction. Okay, so what we're going to show, what we managed to show, is that if you have a protocol that computes k copies of the function and has, say, t bits of communication, then what you can do is somehow modify this protocol to get from it another protocol that computes only one copy of the function, but uses a lot less communication. Okay? Uses a communication that's less by a factor of square root k. And if you can do this, then this proves that the communication must grow, right? Because if the communication in many copies is too small, you would get a contradiction because you would somehow show that this meant that your original function itself had extremely small communication, smaller than you assumed. Okay, so this is kind of the main thing you need to do. And the way we do this is in two steps. In the first step, we first take the protocol that has t bits of communication and show you can get from it a protocol that still has many bits of communication, but now computes the function on only one copy. But the win that you get is somehow the amount of information that the messages in this protocol carry is very small. Okay? So the amount of information is only t over k bits of information. Okay? And once we have that, in the second step, we show how to take a protocol that has very small information in the messages and compress it to get a protocol that actually has a small amount of communication. Okay? Now, I won't say much about how we measure the information because it's a lot of technical details. But I think our main contribution is kind of the second step, where we kind of show how to do a compression how to compress an interactive protocol. Okay, so and that's what I feel our main contribution is. So you can think of, just to put this in the context, we know traditional compression algorithms, what they kind of do is basically they do the same thing except for protocols that involve only one message, right? So typically what you have is either a file or some transmission, and it's long, but you know that there's only kind of k bits of information in the message. And then we understand very well how to compress it. You can always take this thing and make it into a shorter message or a shorter file that has the same effect, but on average only k bits which is only k bits long on average, right? So you can actually compress it down so that the length of the thing is close to the amount of information that's stored in it. And what we managed to do is kind of generalize this to a more general setting. So now we have a protocol. Okay, so it's not just one message, but an interaction between two parties. And we know that, again, the overall information in this protocol is small. And somehow what we managed to do is, again, compress it to get a new protocol where the overall communication is close to what it should be. Okay, I don't know any applications for this, but it seems like it should be useful.
Question? Yeah, but how do you know that the total information in the protocol is small if the function is arbitrary?
So we start from the assumption that, first of all, the information does, okay, so yeah, I didn't really explain all the details, but when I'm talking about information here, I'm talking about kind of, I don't care what the function is. All I care about is the correlation of the messages with the inputs. Okay, so I'm measuring actually how much information do the messages carry about the inputs. And that's all I'm trying to simulate. So I'm starting from the assumption that the original protocol is really good at computing the function. So I'm just trying to simulate that protocol. So I don't really look at what the function is about. So I just want to say, so the first way you might think of doing what we do is you might look at what's on top and you say, okay, we already know how to compress individual messages. So what we should do is kind of look at this protocol and compress every message that's being sent in this protocol. Okay, but kind of the problem if you try to do that is if you're in the situation that this protocol has so little information that kind of every message has less than 1 bit of information, you're going to have to transmit at least 1 bit for every message that's here, and this would already be too much of a loss in the kind of thing that we're trying to do. So somehow what we achieve is we manage to do this by losing, without paying for this. So we manage to compress messages even across rounds. Okay. Okay, so that's all I wanted to say about that. I'm going to jump to something else, to hardness of approximation. Okay, so this is a whole area of research with a lot of work in the last 15 or 20 years. But let me kind of try to just give you a big overview. Okay, so we've known for a long time now that many combinatorial problems that we want to solve are actually very hard to solve, right? So if you want to find an algorithm that solves these problems exactly, you cannot do this unless p is equal to np. Okay, but you could ask the question, maybe it's enough just to solve these problems approximately. Okay, so maybe you don't want to find, say the exact route for the traveling salesman in your instance, but you'd be happy with a route that's, say, within a factor of 10 of the best answer. So the question is, so can you do this? Can you find approximate answers? And starting in the early 90s, it started to become clear that for many of these problems, actually even approximating the answer is hard. So for many of these problems, you could show that even if you try to find an approximate answer, there's no efficient algorithm that can do it unless p equals np. Okay, so I kind of this is a huge body of work, and I only left myself a little corner for references. I think the most important development in this whole kind of in building this picture was the proof of the Pcp theorem, which happened sometime in the early 90s. Okay, so let me just kind of give you a kind of a high-level idea of how you would prove such a hardness of approximation result. Okay, so let's say, for instance, that you want to prove that it's hard to approximate the number of clauses that can be satisfied in a SAT formula. Okay, so that's a SAT formula. It's in CNF form, so you have a bunch of clauses, and the formula is the AND of these clauses. And we know that it's NP hard to distinguish to tell whether or not this formula has a satisfying assignment. Okay, whether or not all the clauses can be satisfied in this formula. Okay, so so I've drawn this picture where I've arranged all the SAT formulas on this line, okay, according to the fraction of their clauses that can be satisfied. So all the clauses which are all the formulas which are satisfiable are at the top, at the 1, and anything that's below there is a formula where you can't satisfy all the clauses at the same time. Okay, so kind of what we know, what we're starting out from, is the assumption that it's hard to distinguish two formulas that are like this. You know, a formula that's satisfiable from one that's below the top. Okay, to prove a hardness of approximation result, what you really need to do is find an efficient algorithm that can do what's called gap amplification. So let me show you what that is. What you need is an efficient algorithm that can kind of take a formula and mangle it, okay, to produce a new formula with the following properties. Okay. If the formula that you started out with was satisfiable, then what you want is that the mangled formula that you get is also satisfiable. It stays at the top. And on the other hand, if the formula that you started out with is not satisfiable, then what you want is that the new mangled formula becomes really, really far from being satisfiable. Okay, so you can't even satisfy 1% of its clauses. Now, if you could do this, we'd be in really good shape, because you could take because any algorithm that can distinguish two formulas of the type on the right can be used now to distinguish two formulas on the left. Right? So if you had an algorithm that could distinguish H1 and H2, you could first run this gap amplification algorithm to convert F1 to H1, F2 to H2, and then run your distinguisher for H1 and H2. Okay? And so this kind of shows that it's actually hard to approximate the fraction of satisfiable clauses, because to distinguish two formulas that are on the right, all you need is an approximation algorithm, right? All you need to be able to do is say approximate the fraction of satisfiable clauses within a factor of 10, right? Because there's such a big gap between these two formulas. Okay, so that's kind of the high-level scheme. So everything to prove that it's hard to approximate things, all you need to be able to do is get algorithms that can do this gap amplification. Okay. Now, at first, you might think that. Let me say that what I said isn't just restricted to SAT formulas, right? It's just a general framework. You could apply the same thing to any optimization problem, right? So if you were, for instance, interested in proving that it's hard to approximate the fraction of edges that can be properly colored in a 3 coloring, then you would try and do the same thing, except now you'd be trying to mangle graphs so that the gap is widened. Okay, so the same idea works for every problem. And at first you might think that if you figure out how to do gap amplification for problem A, then this tells you nothing about how to do gap amplification for problem B. Okay, but it turns out an important step in doing this stuff was when people figured out there's actually kind of a common mother problem that you could do gap amplification for that would solve the issue for a large class of combinatorial problems. Okay, so let me just explain this with an example. So so here's a SAT formula, and what we're interested in doing is calculating this number alpha, which is a fraction of the clauses that can be satisfied in the best assignment to this formula. Now it turns out you can from this formula you can define a certain kind of game. Okay, the game is played between two players who are not allowed to communicate. Okay, so here are the two players, and let me describe the rules of the game. So when the game starts, a referee samples from this formula two things. She samples first a random clause from the formula, and then a random variable from the clause that was sampled. Okay. And then the players, when they play the game, have to respond with assignments to the variables that they were asked about. Okay. And finally, the referee just checks that the assignments that she got back, first, they satisfy the clause that she asked about, and second, that the players gave consistent assignments to the common variable. Okay? Anyway, so associated with this fixed formula is this two-player game, and you can do this for any SAT formula. And the really interesting thing is that it turns out that this parameter that we're interested in, alpha, is closely related to the best success probability that the players can hope for in this game. Okay, so it doesn't matter exactly what the relationship is, but kind of if you want to estimate this parameter alpha, it's somehow enough to estimate the probability of success that the players have in this game. Okay, and this phenomenon is not just restricted to the problem of SAT. It turns out that it works for many other problems. So I won't get into the details for this one, but it turns out that for many problems, estimating the optimization parameter that you're interested in is the same as estimating the success probability of the players in this kind of game. Okay, so this connection meant that if you want to prove hardness of approximation results for many different problems, you don't need to figure out how to mangle formulas or graphs or anything like this. All you need to do is figure out how to mangle these games. Okay, all you need to do is to be able to take a game and somehow change it so that if the game had the property that the players always win, then the new mangled game also has the property that the players always win. And if the game had the property that the players sometimes lose, then the mangled game has the property that the players lose, a lot of the time. Okay. Okay, so that's kind of the core of the issue. Okay, so now we just need to figure out how to do this, how to mangle the game, how to make the game harder. And this is where again we're going to see a question about direct sum. It's very similar to the type of question we saw before. So here's a game. In general, the way it works is, the referee is going to ask the players some questions, and then the players are going to respond with some answers, and the referee checks something. And we want to make this game harder, right? So how can you make this game harder? Maybe the first thing you would think about is, well, the referee should just ask more questions, right? Instead of just asking one pair of questions, the referee should kind of repeat this game in parallel. So the referee should ask, say now, two questions, both sampled according to the same distribution, send both of those to the players, and have the players respond now with pairs of answers that have to do with each of the questions that they were asked about. Okay? So this seems like a natural candidate for making the game harder. You see that if the players could always win the original game, then they can always win the new game because they know how to answer every question. And you'd hope that if they have some chance of losing the original game, then their chance of losing should go up in the new game. Okay, so the chance that they get a hard question should be higher. Okay, so that's a question. The question then is, does this actually work? And this turned out to be a pretty tricky question. There were several attempts at trying to prove that something like this works. It turned out to be elusive. In fact, people found a lot of evidence that said that it doesn't work. Okay, so they found examples of contrived games for which, if you repeated it, say 5 times, the chance of success of the players does not go down. Okay, but somehow if you repeat it 6 times, it does go down. So it wasn't clear that it doesn't work. Okay, until in '94, Raz, in a really beautiful proof, showed that actually it does work. So if you repeat the game enough times, the value of the game does, the probability of success of the players does go down. Okay. Okay, so this was so this allowed us to complete the picture. Okay. This allowed us to complete the picture. So if you kind of want to prove hardness approximation results, the way we know how to do this today is involves exactly a parallel repetition. Okay, so you kind of start from the assumption. You first prove that it's hard to strongly approximate the value of the probability of success in the games. Then you use parallel repetition to amplify the gap. And then finally, there's reductions from the assumption that it's hard to weakly approximate games to proving many, many hardness approximation results. Okay, so that's kind of the big picture of the things that we know. And so recently, in about 2001, 2002, a big development in this area was the unique games conjecture of code. Okay, so he made a conjecture about the hardness of approximating the value of games, the probability of success in games. And the reason it's so important is that kind of if this conjecture was true, it turns out that it would show that many, many algorithms that we have for approximation problems are already, best possible. It would imply that improving any of the algorithms for these problems is impossible unless p is equal to np. Okay, but it's only a conjecture. We still don't know how to prove it. Okay, but if you tried to prove it, you might look at the picture on the left and say, well, what we need to do is we need to first figure out how to do this step, the gap amplification step. We need to figure out how to take games of this new type and somehow amplify the gap. Okay, unfortunately, Raz's parallel repetition theorem, the gap amplification theorem that I talked about, is not strong enough to apply in this situation. Okay, and this is kind of where I came in. I managed to show that to show how to improve the theorem about gap amplification in the situation to get something that is strong enough to help in this situation. Okay, and so the end result now is that we now have one more step towards proving this conjecture, and now all that's left to get these optimal hardness approximation results is to prove the weaker statement at the top there. It says it says something weaker. Okay, so that's kind of my contribution in this area. Okay, so I want to move on to the last part. I want to tell you something about foams. Okay, so this is foam. It's what you get when you blow a bunch of bubbles and put them together. And since we're computer scientists, when we look at a picture like this, the first question we ask is, what optimization problem is this thing trying to solve? Right? Okay, so what optimization problem is it trying to solve? Okay, so it's a hard problem. It looks complicated, so we should first look at special cases. So here's a special case. It's just a single bubble, and we all know what problem this is trying to solve. here's the problem. The bubble is trying to minimize its surface area, right? It's all pulling in, but it can't squish down to a point because it has some fixed volume and the air can't escape. So there's a constraint that its volume is fixed to something, okay? And we know exactly what this thing is trying to be, right? It's trying to be a sphere because this is the shape that minimizes the surface area for a fixed volume, okay? Now the problem we're interested in is harder, okay? Again, each of these pieces is trying to minimize its surface area, but now not only does each piece have a fixed volume, kind of all the pieces have to fit together to tile the space, right? So they can't all be spheres because they wouldn't fit together. And if you put spheres together, the gaps would not be spheres, right? Okay, so so this is a question that we're interested in. You know, try to figure out what is this thing trying to be. Okay, what's the best shape that does this? Okay, and again, to understand this, I'm going to look at a special case again. So I'll only look at periodic forms. So here's the plane, and I've drawn, here are all the points which have integer coordinates. Okay, so they're all the points that are shifts of integers. And I'll say that a body gives a periodic form if it has the property that when you take this body and translate it by integer shifts, what you get is something that fills the whole space. Okay, so that's integer periodic form. And now the question I want to ask, inspired by the bubbles, is what's the best such thing? So what's the minimum surface area of a body that tiles d-dimensional space with according to these integer periods? Okay. Okay, so so it's easy to see that any body that does this must have kind of volume 1 because you're shifting it by 1 every time. And so that means that the best body must have surface area that's at least as large as the sphere of volume 1, okay, which is something that behaves like square root d. Okay, but of course the sphere does not tile the space, so it's not the right answer. On the other hand, we do know something that does tile the space. That's the cube, and this has volume. This has surface area that behaves like 2D, so it's linear in D. The question is, what's the right answer? And last year, in work with Kindler, O'Donnell, and Wigderson, we managed to show that the answer is actually a lot closer to the sphere. Okay, so what we got is we showed that there is a body that tiles according to the integers. At the same time, its volume is something that's order square root d. Okay, since in fact it's only 3 times bigger, I think, or roughly 3 times bigger than the volume, the surface area of the sphere. Okay, so you do have a body that has a small surface area comparable to that of the sphere, but still tiles according to the integers. And surprisingly, this result, the way we showed this, all the ideas kind of came out of the study of parallel repetition, the study of the results in hardness of approximation that I talked about. Although at first sight you might think that it has nothing to do with computer science and hardness of approximation, all the ideas somehow came from there. Okay. Okay, so that's kind of all I wanted to say. So another thing we got out of this work was a nice way to round points. Let me just explain that to you. So we also learned of a way to round points in Euclidean space to points with integer coordinates that kind of have these two opposing qualities. First of all, if you look at any point and look at where it's rounded to, no coordinate of a point is changed by more than 1. Okay, so you can kind of round these points to integer coordinates so that no point is changed by 1. And on the other hand, if 2 points are close by, the probability that you separate them, you round them to different points, is really small. Okay? So the chance that 2 points get rounded to different points is proportional to the distance between them. Okay, so this is another nice thing that came out of this that wasn't clear how to do before. Okay. Okay, so that's all I want to say about foams. Let me just say a few things about other problems that I think are related to this line of questioning. So one thing that looks very related is trying to prove direct sum for streaming algorithms. So you can imagine that you have some streaming algorithm developed. So you have an algorithm that uses very small resources, say very small memory, and is looking at a lot of data that goes by. And you measure the cost of this algorithm in terms of the amount of memory that it needs to perform whatever task on this big stream. And now the question is, suppose you don't have just one stream coming in, but many streams. Okay, do you really need to use many more times the memory? Okay, and it looks like many of the ideas that we developed for the studying communication complexity apply also in this setting. So that's one of the things I'm trying to work on. And of course, I already talked a little bit about this. What we do is we find a compression scheme for interactions, and it would be interesting to find better compressions or even applications for this kind of thing. Okay, and I talked about one way to amplify the gap for problems, and it could be possible that there are much simpler ways that would be easier to understand, and that's an important open problem. Okay, and finally, a very important problem, I think, is to close off the second line of work with hardness of approximation and try and get a proof for the unique games conjecture that would give us a lot of hardness approximation results. Thanks.
Is this mic on now? Yes, it's on. Okay. So do we have any questions for Noop? Pedro?
Yes.
So why did you make this assumption that your bubbles have to enclose points on an integer lattice? That's not the case with the real lattice. In fact, the function could have very widely different sizes of bubbles.
Right. It was just, if I didn't say it, I should say that it was just a simplifying assumption that would actually allow us to ask a question that we can reason about.
And so you couldn't do that with, say, having some random, you put down random points, right? And then
well, so maybe the next generalization is trying to find it for any lattice, not just the integer lattice. And actually, we do have results for that setting also. Now, if you just give me arbitrary points, which with no structure, it's kind of hard to say anything nice, because it really matters where the points are. I mean, it's hard to define it.
An diagram of those points, right? And
right, sure.
Maybe your bubbles will approximate that.
Yeah, but you should have a small way to describe the points. So a lattice seems like the most natural way to describe a lot of points.
Any other questions?
Can you give us some idea about what the shapes are, at least in small dimensions, of the upper boundary?
Actually, they look like really bad shapes that shouldn't give the right answer. In fact, the situation is not maybe as nice as you might have guessed from what I said. We don't actually have a fixed shape that does a job. What we actually found is that there's a distribution on shapes, okay, all of which tile the space properly, and the expected surface area of a random shape according to this distribution has a small surface area. So I don't have actually a fixed shape, but I just know that there is a shape that works.
It's an existence proof.
It's a proof of existence. I can't give you a formula for a shape or draw it.
So you were saying in the communications portion that to get this fewer communications bits, you added some sort of compression to it. Now, it would seem to me that that compression would correspond to some sort of prior sharing of information between the two entities, so they know the compression protocol. How does that factor into, is that repeated complexity, or does that just, do you kind of ignore that?
Exactly, let's forget about protocols and just traditional compression. It's the same setting. So you always have some prior information about the distribution of, say, the files that you're trying to compress. Okay? So the reason you can compress a file, say a text file, is because you know that the information that's in there is not completely uniformly random. There's some distribution, and you try and compress it to take advantage of the knowledge that you have about this distribution. So it's the same setting. Does that answer your question? Or? So you do know kind of the distribution of the messages in this protocol. And this is what you're going to use to compress the messages that you want to transmit. Okay, and this is necessary. If you knew nothing about it, then you wouldn't be able to compress anything. Then the information would be really high, so you wouldn't be able to compress anything.
Any other pressing questions?
In the communication complexity, how tight are the bounds, both for deterministic and randomized?
They're both not tight. So we should hope, and you kind of go back and forth between the beliefs that. So you should hope that that computing k times as much should take you k times the resources. And what we show is it takes square root k times the resources. And it's not clear what the right answer is. I think it should be k times, but I don't have a good reason to.
All right. Well, let's take the rest of the questions offline. Let's thank Anoop again.